My name is Doug Santry, and I did this work with Kaladhar for Voruganti at NetApp. And I'm going to talk to you today about Violet, which is a byte-oriented userland storage stack. So this is just the outline of the talk. I'll motivate my work. Then I'll describe the prototype, share some results, and conclude. So the motivation. So over the last couple of years, right, it's become clear there's an IOPS tier emerging on the host. Lots of applications are accelerating their performance by installing, for example, host-side flash on the PCI bus and that sort of thing, and skipping the network hop to persist their state. Some applications are taking it even further, and they're keeping their entire working set in DRAM. And this is called in-memory computing or in-memory databases. One of the most famous examples, of course, is SAP's HANA or a number of others. And initially, these were considered very expensive systems, and they were niche, and they were only used for enterprise-critical analytics and that kind of stuff. But that's no longer the case. They're now being used for OLAP, OLTP, DSS, ERP, everything. In particular, for example, SAP wants to replace all of their databases with HANA. That's their strategic direction. And because DRAM is fast, but of course it's also ephemeral, and that leads to a lot of problems, right? You still have to persist your state. And HANA, for example, has a very famous persistence layer. But it's an interesting workload, right? Because they never read. It's a write-only workload. And they still logically log their transactions. That's important, and I'll explain that later. And they're still just using, for the most part, tables and columns, right? After decades and decades of research into algorithms and data structures and that sort of thing, we're still just using columns and tables for the most part, and that's leaving a lot of potential speed up on the table. Because all the speed up of, for example, HANA is you're just running it in RAM. Yeah, it's faster because DRAM's faster. But what you're leaving on the table there is the performance improvements you can get by asymptotically improving performance by using different data structures. I would argue HANA is not that much different than just running MongoDB on a RAM disk. Okay, so let's have a quick look at the memory hierarchy of today as we know it, right? And this is, in particular, I'm talking about applications whose working sets actually fit in main memory. If you're writing, for example, a database and you know that your working set doesn't fit in memory, you have to use a B+ tree or something like that, right? Something that's disk friendly. But if you and I were just going to write a program that was going to fit in memory, right, we wouldn't think in terms of columns and tables. We use the STL. I want a standard map if I need log2 lookup times and that kind of stuff, right? But then when it comes time to actually, we choose our data structures for the convenience of computation. But at some point, right, I need to persist my state, and even a program like this that I'm using right now, PowerPoint, does this, right? It's got the data structures it wants in main memory. The storage system then forces it to inflect its state for the persistence layer, right? So when it comes time to write out my PowerPoint presentation, because I need to persist it, it changes the state, writes it into the kernel, and then it gets written out in form of blocks. Right? And one of the big problems here is because it's left up to the application to perform the physical mapping between its address space in virtual memory and the address space that you find in a file. And so you always do the simple thing, right? So my data that might be in a standard map, I'm going to use an iterator. I'm going to iterate through my standard map, and then I'm going to write it out as an array. And then when I read my data back in, I have to insert that data one at a time into my standard map again, and it's slow. And application writers hate doing this. It's a source of corruption. It's more code to write and that sort of thing. And as we get non-volatile memories in SCM and DRAM becomes persistent, or rather main memory becomes persistent, people are just going to stop doing this because they don't want to do it because it's a pain. And it introduces bugs and all sorts of stuff, right? And the problem here is that you have a byte-oriented world being forced into a mechanical block-oriented world. So I would argue that we need a new persistence layer, and it needs to be byte-oriented, and it needs to take account of what applications really want. We need to divorce the concerns that arise from persisting a data structure from the actual selection of the data structure, so people can use the data structures that they really want to use. So I would argue that the file needs to be further abstracted, and that applications shouldn't see the FBN namespace of a file, and some persistence layer should hide all of that for them and automatically just take their updates from memory and persist it in a convenient way, and so you can use the stuff that you want to use. It should be byte-oriented, and of course, it needs to mask the undesirable artifacts of mechanical disks, right? Applications today have to bend over backwards to use disks. They ask the file system, what's the optimal I/O size? Is it 4K? Is it 8K? And there's a very high penalty for random I/O, for seeking and stuff like that. So Violet, it was a system conceived to address that, right? So we're thinking about in-memory systems today, and we're also thinking about NVM and SCM of tomorrow, because we believe that's coming in a couple of years. So the ideas behind Violet then is we take the anonymous heap that you normally find, or BSS that you normally find in a program today, and we name it. So you now have a named heap. Let's just call it a file. Violet replicates the updates to that memory seamlessly and keeps it consistent and seamlessly and automatically, and applications don't have to worry about any of that kind of stuff. We also provide byte-oriented snapshots and data management. So here's just the overall view of the Violet architecture. So basically you have a number of what we call data sponges. They have locally attached disks. They communicate with applications over a very fast network. There's a master server where these sponges register with the master controller. Applications tell the master controller, I need a file. The master just assembles a replication group for it, and then applications write to the replication group. The Violet library does all of this for applications, and they don't need it. So basically, the application needs to link in the user-level library for Violet. And this is the general architecture on the host for Violet. The application links in the Violet library, and the Violet library is responsible for all the I/O. And the I/O goes directly to the replication group and circumvents the kernel completely. So the control path, of course, still goes to the kernel, but everything else circumvents the kernel completely, and the data path is now just through userland out into the network. And the application can use whatever data structures they might want, sparse matrices, Voronoi diagrams, or any other kind of graphs you want, and the persistence layer of Violet does all the hard work for you. And we would argue that this isn't just desirable for today, this is inevitable, right? When SCM and NVM come along, nobody's going to go into the kernel for everything because NVM lives in a world of tens of nanoseconds, and talking to the kernel is a world of microseconds. So this is going to happen no matter what, whether it's Violet or something else. OK, so on the host, in the Violet library, we need a way for applications to express memory updates to the system. And what we've chosen, we've identified two trends and just sort of taken the confluence of them to build the interface to Violet, right? So the first one, there's a C++ standard working its way through the system at the moment. IBM, Intel, HP, Oracle, but a lot of powerful names are driving this standard. And so C++ is going to have a way of dealing with transactions. It's going to be a first-class citizen in C++. It's going to be a reserved word. So we've got a way of expressing transactions at the language level that's not proprietary. In addition to that, Intel has introduced TSX, which includes a restricted transactional memory. It's a hardware transactional memory. And this provides the machinery of actually executing transactions. Intel is also, of course, behind this. You can put the two together, right, and realize that compilers are going to be using TSX in the very, very near future. So Violet has a tool chain then. We have a compiler which compiles the application. You have to run our preassembler processor. We then run it through the assembler, and then you have to link in the Violet library. We modified a Clang++ compiler to recognize the new transaction keyword in C++. When Clang implements this, we will stop doing this. We're not in the compiler game. And we instrument the code with a preassembler tool. This lets us support any compiler and even any language without any changes to the application. So here's an example of a C++ piece of code and how Violet would instrument it to support updating it. So this is just a simple inserting a node into a linked list. I've elided all the edge cases and stuff like that. So in red is the new C++ keyword, transaction. Everything inside those braces is executed with atomicity, consistency, and isolation, just not durability. In green is the violet new operator. We have to control the heap because we're now managing memory for you because we're keeping it consistent for you. The compiler will then emit code. Xbegin is the Intel RTM machine instruction that means begin a transaction. Xend means end a transaction. If you get to Xend, your transaction's completed and accepted and visible to everything else in main memory. And after all the memory assignments, you'll see that we've actually inserted an add to write set. And that is where we take the address that's being assigned to and we verify that it's actually in the heap that we care about. If it's in the heap that we care about, then we are going to propagate the update to this memory location across the network and persist it for you. And there's an artifact of TSX, and that is that you cannot make system calls or anything else. There's lots of other restrictions. Or the transaction will be aborted, and that includes a preemption from the operating system. So even if you write a single-threaded program and you're just updating a single integer as a global variable, you will see transaction aborts because even just preemption is going to cause transaction aborts. So there's millions of little things you have to worry about here. But the result is that because we can't make system calls inside the transaction today, there is actually a non-zero RPO. There's a window of failure here because at Xend, the changes you've made to memory are visible to all of the threads, and people are going to start seeing it and using it. But we actually haven't persisted it yet. We haven't sent it over the network yet because we can't, because the Intel machine instructions won't let us. But when this is NVM or SCM, this won't matter because it's persisted in main memory already. So even though there is a window of failure, Violet does guarantee to keep the durable image consistent. So we maintain two variables inside the library. One is a monotonically increasing serial number. Each transaction receives a serial number. And then the consistency point is there's a sorry, you're just throwing me off. Better go here then. Okay. Anyway, yeah. So we just persist things that way. So I'm just going to skip ahead to Fibonacci array. So we need something on the other end of the wire and the data sponge to absorb all the updates to memory. And just a normal file system is not going to do the job, right? Because when you're inserting stuff into, for example, linked lists, you're talking about tons of tiny little updates, right? Like an 8-byte update to a pointer in a page. You cannot do I/O at the page granularity because nobody can keep up. So we have something that we call a Fibonacci array, and it takes all these random updates that are tiny and scattered all over the address space, and we turn that into a single stream because while disks cannot handle random seeking very well, write bandwidth sequentially written to a disk is half decent. So what we want to do is maximize the amortization of the write cost, right? So 1 over the actual write size is best, 1 is worst, right? So updating a single datum in a B+ tree node, that's the worst because your write cost is 1. We want to avoid that. So what we actually send over the wire are patches, which include the address, the length of the update, and the actual data. We sort these by address, and then we write them out to the Fibonacci array. We accumulate them in a piece of NVM, and then we write them out to disk in those pieces. We alternate between the first levels, and then when two neighboring levels are occupied, we merge them. It's trivial because they're sorted by memory order already, and we just keep doing this. And because each level is the sum of the two previous levels, it's just naturally Fibonacci. And so the height of the file is log 1.6 because that's the golden ratio, which is the Fibonacci array, what it converges to. And we also support Fibonacci array snapshots. So if you look at a Fibonacci array, the data that a memory address could have an entry on each level. So the correct version of a piece of memory is the lowest level in the array. So we could have an entry for address 100 in the first level, the third level, and the 8th level here. And it's not unlikely at all, but the fact that we know that because these are sorted by age, we know that the correct entry is the first entry we encounter in the array, and that's the correct one. And this is the basis of snapshots. So here we have a snapshot where all we do is we copy the array and make the things it points to immutable. And then when it's actually time in the active array to write out a new entry to the Fibonacci array, it's not copy on write. That new entry is nothing but is 100% new information, and it's correct because we know it's the youngest and the newest, and so everything else in all the other arrays is obviated. And I'm just going to jump to some results very quickly because I'm running out of time. So here's the instrumentation overhead. So we ran our stuff without instrumentation and with instrumentation. As you can see, the difference between the two curves is actually really quite minimal. This is because everything that we need is usually in the CPU cache, and it's really quite trivial. It's a couple of integer comparisons to determine whether an address falls into a range. This is the kind of throughput we were getting if we were replicating asynchronously. In which case, that's when we're just filling up Ethernet frames and sending them out over the wire, as opposed to a synchronous two-phase commit. Right? So you can actually stop the application at the end of each C++ transaction and make it wait for confirmation that it's been made durable. But on Ethernet, that's just not feasible, we've discovered. The round trip time over Ethernet is around 250 microseconds. And transactions are on the order of 100 nanoseconds. And the two worlds just don't work together at all. Fibonacci arrays, we compared a Fibonacci array to just staging into a naive file where you have to read the page in, update the bytes, write the page back out. The throughput was absolutely abysmal. With the Fibonacci array, we consistently got around 60 megabytes a second, and with the naive file, it's not 0, it just looks like that on the scale, but it's less than 1 megabyte per second. And restore time is very important for in-memory databases. This is a real pain point for them. So as you can see, by adding data sponges to the system and increasing the size of the replication group, we actually do manage to decrease restore time quite nicely. So in conclusion, the Violet system was designed to divorce data structure, selection, and persistence, and let you actually choose your data structure based on asymptotic considerations and not the difficulty of persisting them to stable store. It provides end-to-end byte-oriented data management and updates, which makes better use of the network and better use of storage on the back end. It circumvents the kernel and the data path. This is inevitable when SCM comes here anyway, because nobody's going to want to use the kernel. And if you're interested in this, or you have an application that you would be interested in using stuff like this, we'd really love to collaborate with you. So please come and talk to me during one of the breaks, and hopefully there are a couple minutes for QA.
Hi. How would you compare them against disk-backed data structures such as level DB or mapDB? Have you considered comparing against them? Although they are, I would say, more single-threaded application or single-threaded work in a single-thread environment, but how would you compare against them in terms of your work?
I don't think I quite understood the question.
So level DB and mapDB and other such data structures, what they do is they provide a vision of that you have in memory a data structure, and you don't have to worry about whether it flows to disk, whether its size grows too big or whatever it is. So everything happens behind the scenes where they serialize data onto a disk and they get back it from the disk and maintain all those data structures. Same thing like your heap thing over here. So I was just asking, how would you compare, or do you think that what could be the difference against such strategy?
Yeah. So I think they're completely different. Level DB is a key value store, and it's a database, right? So you'd build something like Level DB with this if you want to do something more interesting than just a key value store, if that makes sense, right? So Level DB is a database that has a persistence layer. Mm-hmm. This is a persistence layer. So if you're building a DB, then you might be interested in using a persistence layer like this.
I see.
Right, okay. But Level DB is a good example of, well, we can make key value stores because they're easy and we know how to persist them. If you want to do something a little bit more difficult, and it's difficult to do today, with a different data structure, then you might be interested in something like this. makes sense.
Okay, yeah, that makes sense. Thanks.
This is Pradeep from George Washington University, an ex-NetAppian. So I have a question on like this data store is basically you're binding it with virtual memory address, and then you'll be persisting again those virtual memory address. Like you never convert it to physical memory address. So I mean, when you have the data on the disk, and if your system crashes, you would like to restore it to again in-memory data structure. So you're basically binding it to virtual memory address. So what happens if there's a collision in the virtual addresses, or you may want to share this data with another application where that virtual address is already occupied?
Yeah, so you have to, I mean, in our prototype, you have to map it into the same place every time. There are also games you can play with Intel processors and segment registers and segment addressing, which slows it down a little bit so you could get around it that way. Yeah, that is a problem.
Okay. And another question is on recovery. So basically, let's say a memory is being freed. So do you log it on the disk again?
Pardon me, I don't think
so. You have a data structure, let's say a list, and you deleted a node on that.
Okay.
So do you log it?
So no, there's no logging in this. So you'll notice that in that little piece of that example code, the new operator is inside the transactional braces.
Yeah.
And so even allocations from the heap are just a part of the transaction, and so are deletes.
Okay. So then.
So it all happens transactionally.
So if you have so if you have like multiple.
I think he's suggesting we take this offline.
Oh, okay. Yeah.